Good afternoon, everybody. I'm here to present my research titled The Potential of Building Integrated Photovoltaics in Jaffna, Sri Lanka. I am THUSHINI MENDIS, a current PhD student at Huazhong University of Science and Technology in Wuhan, China, and a lecturer at Kotelawala Defense University, Sri Lanka. This is the summary of what this presentation will consist of. I will start off with an introduction, explore the reasons for utilizing building integrated photovoltaics, or BIPV, and look into the current studies that have been carried out on solar potential and BIPV. Then, I will provide you with the background on the location of the study it was done in, and examine the reasons for choosing this location. The methodology used in order to conduct this research will be broken down in detail, and then the results will be presented and discussed. Finally, I will provide a conclusion and summarization of the work. It is now a widely accepted fact that there is an ever-increasing use of fossil fuel energy, which is fueling climate change and global warming, and that these non-renewable energy sources are being used at rates which, if continued, would have its sources depleted. The construction sector plays a large role in the release of CO2 into the atmosphere, which is causing global warming, and in addition, there has been a rapid development and expansion of urban spaces, which is expected to continue in future decades. Furthermore, in recent years, energy consumption has been steadily increasing in residential buildings due to the improved standards of living of urban residents. As of recent, BIPV has started becoming more and more attractive as a solution to these issues. So why BIPV? First of all, it is a versatile technology that allows on-site energy production and use, which minimizes energy losses due to transformation and transmission, since sunlight is universally available. In addition, it does not increase the footprint on the land. Furthermore, PV devices contain no moving points and therefore won't be worn out. And finally, as a technology, it is extremely flexible and can be used in other building products like solar roof tiles, decorative screens, and curtain walls, which allow the replacement of conventional building materials in the building fabric. There are many existing studies which have been carried out relating to the quantification of solar potential in the built environment, some of which were focused on examining the effects of various horizontal and vertical building layouts on solar potential, and some analyzed the effects of various urban density parameters, such as site coverage, plot ratio, and building density. The selected location for the study was Jaffna, Sri Lanka. Sri Lanka is a small tropical island in the middle of the Indian Ocean with plentiful year-round sunshine. Currently, hydropower is the main source of renewable electricity generation, which accounts for only 27.9% of the total power generation. Photovoltaics are still in the early stages of implementation, and there exists a possibility of implementing government tariffs in order to encourage PV utilization to achieve total electrification of the country by BIPV and grid hydropower. So why would Sri Lanka benefit from BIPV? Currently, the total energy requirement in Sri Lanka is about 11,000 kilotons of oil equivalent, where only 56% of this is from indigenous resources, and the rest of the 44% have to be imported fuels, which cost the country approximately $5 billion in foreign exchange. This is 25% of the total import expenditure and a staggering 50% of total export income. Furthermore, Sri Lanka's largest power station, which is the Norachalai power station, has faced several breakdowns, which have caused frequent island-wide power outages, and this has forced the country to be put into controlled regional power outages in order to meet the power demand. In addition, the overall annual electricity demand of the country is expected to grow by about 4 to 6%, which needs to be met in the future. But as of now, there are no such plans that have been put in motion in order to meet this increasing demand. Finally, the country has set forth certain green objectives which need to be met. These include increasing the share of electricity generation from renewable energy sources from 50% in 2014 to 60% by 2020, reducing the carbon footprint of the energy sector by 5% by the year 2025, and finally becoming an energy self-sufficient nation by 2030. Here you can see a view of the urban context in Colombo, Sri Lanka. This was the framework utilized in order to conduct this research. A solar analysis was done using the Irradiation simulation engine with a 3D model of a residential block in Jaffna. Then, by applying specific technical parameters, the solar potential and PV potential were calculated, and finally an economic analysis was conducted. In order to obtain the 3D model of the block, Google Earth was utilized in order to map the building footprints, which were modeled three-dimensionally on Google Sketchup. For the purposes of this research, it was necessary to determine a suitable tool that could be used for solar irradiation estimation. Radiance is a highly accurate ray tracing software system, which applies the Perez diffuse radiation model. This software has been authenticated many times and successfully utilized in many applications regarding the assessment of solar potential on building roofs and facades for daylighting and electricity generation. Therefore, radiance was chosen as the method to estimate solar radiation for this research, and it was integrated as a plugin in Rhinoceros 5, which could be used via the Grasshopper interface and the Ladybug and Honeybee tools. These help to investigate and assess the environmental performance, where Ladybug imports standard Energy Plus weather files into Grasshopper. It then supports the preliminary stages of design and the decision-making process by supplying a range of 3D interactive graphics. Honeybee connects the visual programming environment of Grasshopper to 4 simulation engines which allow to run a solar irradiation analysis. This was the block of residential buildings that was selected from Jaffna, which was then mapped and modeled on Google SketchUp. This 3D model was then imported onto Rhinoceros, where the solar irradiation simulations were run. The results obtained are visualized here. As you can notice, the roofs shown in red represent areas receiving high amounts of solar irradiation, and those in yellow represent lower amounts of irradiation. The results obtained were then disseminated and are shown in the following table that I will go into in detail. The achieved results exhibited high levels of irradiation with over 1,500 kilowatt hours per meter squared of solar irradiation incident upon all building roofs. The average solar irradiation across the roofs was 1,827.4 kilowatt hours per square meter, and the average household has a roof area of 204.3 square meters. This tells us that the total solar irradiation incident upon an average household is 373 megawatt hours. If we consider a PV panel efficiency of 15%, just 15%, the total electricity production of a household could be 56 megawatt hours. And considering a carbon dioxide emissions factor of 0.71 kilograms of carbon dioxide per kilowatt hour for electricity, a total of 6,816 kilograms of CO2 emission savings could be achieved by implementing PV on a single residential roof per year. Considering an annual electricity consumption of 9,600 kilowatt hours, it was calculated that each year 396,000 rupees could be saved on grid electricity. By referring to current PV prices in Sri Lanka, it was assumed that the installation cost of a PV system would be 1.8 million rupees. And considering the electricity cost savings, it was deduced that the initial investment could be recovered by the 5th year. Furthermore, it was discovered that by the 10th year, a 100% profit could be made on the investment. So in conclusion, the purpose of this research was to evaluate the PV potential of residential buildings in Jaffna, Sri Lanka, which was done by utilizing the Irradiation simulation engine and the Grasshopper interface. The results obtained showed a high potential for BIPV implementation in the region, with the break-even point by year 5 and an achievement of 100% profit on the investment by year 10. Although careful consideration was taken in order to make this research as accurate as possible, it was noted that there were a few inconsistencies. Firstly, there existed a slight inaccuracy when mapping building footprints using Google Earth due to the low-resolution images available in the region. And secondly, the area consisted of several large trees which were not accounted for and could cause serious shading on building roofs. Plans and suggestions for future work and research include the mapping of these trees in order to consider for shading on roofs when estimating solar potential. Thank you for listening.